Our next unit is on vectors and dot products. Well, we already know about vectors, so I've given you a couple vectors here, vector u and vector v. Now, what is this idea of a dot product? Well, let's just remind ourselves of the vector operations we know. We know to add two vectors together, we can simply add the first coordinates together and the second coordinates together. So u plus v would be the new vector 4, 3. We know that scalar multiplication means you take some number times a vector, which would give us something like our new vector 15 and negative 12. Notice, when we add vectors, we get a vector. When we multiply a vector by a number, we get a vector. Now, a dot product, here's what a dot product is. To find a dot product, what we do is we multiply the first coordinates together, 5 times negative 1. I'll write that all out, 5 times negative 1. And then we add to it what we get when we multiply the second coordinate, so negative 4 times 7. 5 times negative 1 is negative 5. Negative 4 times 7 is negative 28. The dot product of these two vectors is negative 33. Notice, when you find the dot product of two vectors, you do not get a vector, you get a number answer. Now, what does a dot product mean? It's really hard to explain, and in fact, the best explanation I can give you is that the dot product really has very little meaning on its own, but it is useful for finding other things. Okay, so we can use the dot product to find a whole bunch of different information, but on its own, this number, negative 33, has very little meaning. It does mean something, but it's really, really hard to describe, hard to make meaning of this. But if we know how to find the dot product of two vectors, we can find a lot of other information. So today's unit is on what other information we can find if we can find a dot product. So let's get into some of that. Now, there are some properties of dot products, and I'm not going to have you write these down. Don't dwell on these. Basically, if you change the order of a dot product, you'll get the same value in the end. The dot product of 0 on any vector is going to be 0, etc., etc. This last one may be useful. Dot product of a vector in itself is the magnitude of the vector squared. Or you can flip things around and say, hey, the magnitude of any vector equals the square root of the dot product of the vector and itself. Okay, let's use that one right away. First example says find the length of u. Now, we could do what I just had up there. To find the length of u, we know that the magnitude of u is equal to the square root of the dot product of u and itself. So dot product, I'm just going to write this out again so we can find the dot product of u and itself. Dot product means multiply the first two terms together, 2 times 2 is 4, plus multiply the second 2, you get 36, and the square root of that is the length, or the magnitude of vector u, which you can write, that's 4 times 10, so it's like 2 square root of 10. Now, is this something you have to know? Absolutely not. We already knew that we could find the magnitude or length of u by using the Pythagorean theorem. So this is nothing new. Okay, so let's get into something that is new. All right, this formula up here, something we definitely need to know, so definitely get that down. And look what this formula is. It's to find the angle between two vectors. Okay, so I'm going to draw these two vectors. Vector u is 2, 5, and vector v is 4, negative 3. Let's just make a sketch of these. So I'm going to just say vector u goes 2 to the right, 5 up. Here's vector u. Vector v goes 4 to the right and 3 up. So here's vector v. Here's what this formula tells us. It tells us the angle between these vectors. It tells us this here. I'm going to label it theta. Okay, so let's see what we can do here. So I'm going to say the cosine of theta equals u dot v. Well, dot product means multiply the x's together. That gives me 8. And multiply the y's together, the second coordinates, that's 15, and add those together. Over The magnitude of u. Well, I can use Pythagorean theorem here to find the magnitude of u. That's going to be 2 squared plus 5 squared. That's 4 plus 25. That's going to be the square root of 29 times the magnitude of v. Well, we have 4 here and 3 here. 4 squared is 16. 3 squared is 9. That's going to be square root of 25, which is 5. Now let me simplify this. So I get the cosine of theta equals 23 over 5 square root of 29. Well, if we take the inverse cosine of both sides, I get theta, that angle, is approximately 31.3 degrees. So to find the angle between two vectors, we can take the dot product of the vectors, divide by the magnitude of each vector multiplied together. Okay, that's a little bit more useful. That's something that we can use here. Okay, a little bit more about this angle between the two vectors. What if we find the dot product of two vectors and we get 0? If we get 0 on top, what does that mean? Well, it means that what we do is we say that those vectors are orthogonal if that dot product equals 0. Now, orthogonal, what on earth does that mean? Well, orthogonal means, in general, it means perpendicular. However, now you might be thinking, if that just means perpendicular, why don't we use the word perpendicular? It means perpendicular, except there's one vector, this one, 0, 0. Now that's a vector that doesn't go anywhere, but this vector is orthogonal to every other vector. So what does orthogonal mean? Orthogonal means perpendicular. However, this 0 vector is also orthogonal to every other vector. Okay, let's get into more uses of dot products. All right, if you've ever taken a physics class, you've probably made drawings like this. So on this drawing, you've got some object, it's on a ramp, and gravity's pulling that object straight down. There is some friction that's pulling that object toward the ramp, and the object will be moving down the ramp along vector v. Now, some things we know. We know that if we add these two vectors together, we get vector u. Here's something new. W1, this vector in this direction down the ramp, is what's called the projection of u onto v. Okay, we're going to be dealing with that, the projection of u onto v. To find that projection, here's what you do. You take the dot product of u and v over the magnitude of v squared times vector v. So everything in parentheses here will give you a number. Multiply that number by whatever vector v is. And then this last part, nothing groundbreaking. It's just really reorganizing this first equation. So the main thing here is to find this vector, w1, projection of u onto v. Here's your formula right here. U dot v over v squared times vector v. So that's our next step. That's what we want to try to do next. So we want to find this projection of u onto v, which on the previous page I called w1. Okay, so let me write that out again. So to find w1, or this projection, it equals u dot v all over the magnitude of v squared times vector v. So what's in parentheses will give us a number. Let's find what that number is. U dot v, to find dot product, we multiply the first coordinates and the second coordinates, and we add those together. Over the magnitude of v squared. Well, to find magnitude, it's Pythagorean theorem. So I can say, okay, negative 2 squared is 4, 6 squared is 36, it's the square root of that. So it's going to be the square root of 40. And then we square that number. times vector v. Well, let's clean things up here. So that's going to be 6 on top. Square root of 40 squared is going to be 40. Or to simplify this fraction, it's 3 over 20 times vector v. Now, 3 over 20 times this vector v, so let me just rewrite this. 3/20 times this vector, negative 2, comma 6. Okay, if I do that, 3/20 times negative 2 is negative 6/20. 3/20 times 6 is 18/20, which I'm just going to rewrite this as negative 3/10 and 9/10. So there's our projection of u onto v. So I can say W1, the projection of u onto v is negative 3/10 and 9/10. Okay, now we also need W2, because we need to write this as the sum of two orthogonal vectors. So to find W2, here's really what we have. We have W1 plus W2 equals u. Now we know u, we know W1, so to find that other missing vector, I can say W2 equals u, what we're given, minus W1. So 3 minus negative 3/10 is going to give me, let's see here, that's like 3 plus 3/10, that's like 3.3, 3 and 3/10. And you can write that as a fraction if you choose. I'm going to choose to write it as a decimal. Next is going to be 2 minus 9/10. 2 minus 0.9 is 1.1. So our orthogonal vector W2 is equal to 3.3, comma 1.1. All right, let's add another new idea. Last new idea. It's something called work. Again, another physics idea. So jot these things down, please. But I'm going to scooch this down a little bit so you can see it a little bit better. Now, if your force is going in the same direction as your movement, work is pretty easy to find. It's the magnitude of the force, the amount of force, times the amount of the direction. However, if your force is going in a different direction, we need to find the projection of that force, which we can use a cosine to find this amount here, or we can use a dot product, the dot product of the force and the direction vector, PQ. So really, depending on the situation, there's a few different ways we could do this. So we're going to look at 3 different examples of this, because there's really 3 different things you might want to do here. So example 4 says find the amount of work needed to lift a 200-pound weight 4 feet. So in this case, we're just taking this weight, whatever it is, I'll draw it right here. Here's 200 pounds. And we're lifting it straight up 4 feet. Well, if the amount of force is the same direction as where the thing's moving, work is pretty easy. We could take the magnitude, which is 4 feet, times the amount of weight in this case, which is 200 pounds. And the amount of work is going to be the product of those two quantities. So 800, my unit here is foot-pounds. And you might be thinking, well, I hope it stays that easy. Well, not quite. So let's say we're dragging this object, and notice we're dragging it at an angle of 15 degrees. We're using 500 pounds of force to drag this, and we're dragging this 900 total feet. So again, if we had everything in a straight line quantity, it's much easier. So let's create a straight line quantity here by using a right triangle. Let's find this distance right here, which I'll call x. And we can use what we know about trigonometry by saying that cosine of 15 degrees equals adjacent over hypotenuse. If we solve that for x, we get that that's going to be about 482, and I'll put a label on that, 482 pounds. Now it's just like the previous example. So the work is at 482 pounds times the distance that we're moving this, which is 900 feet, So if we multiply these quantities, we get about 433,000. And again, my label is foot-pounds. So if we have our force going in a different direction from where this thing's moving, we have to use a little trigonometry to find the force in that direction and then multiply it by the distance. Now what if we have one last example like this, where we don't really have a direction, don't really have a distance. We're moving a particle. So you might have heard about particle physics. Moving some particle from P to Q. The force is this magnitude, is this vector right here. The force is given by vector V. Well, to be honest with you, this is the easiest of the three examples. Now the first thing we have to do is just figure out vector PQ in component form. Remember, to find that we can say, okay, the change in the x's and the change in the y's. So there's vector PQ. We need to find the dot product of vector PQ and vector V. Well, dot product means multiply the first coordinates plus multiply the second coordinates. So your amount of work, now we don't have any units here, amount of work is 17, whatever the unit happens to be. Alright, that wraps up our notes for today. So get a little practice with this on page 445. Notice here this says odds for the first. These last ones, do all these problems, please. So it's not a whole lot of extra problems, but a little practice will do you good.